steps. And actually it is proven that it always converges to a stable solution. So we always reach a stable solution. We can reach different stable solutions from different starting points, sure. However, we always reach a stable solution. So one question is that which stable solution is better, considering that we can reach different stable solutions from different starting points. We are going to talk about that in a bit. And just as an overview, step 1 is about number of clusters. We specify 2 clusters in this example, and then we partition the data points into 2 clusters based on proximity to the centroids that we have chosen randomly, and then we move the centroids to the mean or to the center of gravity of the clusters, and then we cluster again based on the new centroids, and that's it. We repeat this over and over. And I think I explained the example with the kiosks and how they move in a residential area, right? Do you want me to repeat it? No? Are we good? Okay. So the advantages of K-means are its simplicity, its scalability, guarantees convergence. So as I mentioned, it always reaches a stable solution, and it generalizes to clusters of different shapes and sizes. So you are not limited to clusters of, let's say, spherical clusters or cubic clusters. The clusters are determined based on the proximity of the data points to the centroids. And there are 3 main disadvantages, or let's say there are 3 concerns regarding the K-means method, and we address all the 3 concerns here. First of all, the outliers can just move the clusters, can change the clusters heavily, because remember, we are clustering based on the proximity of the observations to the centroids, and proximity is in terms of Euclidean distances. So Euclidean distances are sensitive to long distances, and so what we do is that we square the distances. We minimize the squared distances, essentially. It is, in some sense, it is similar to least squares method. And when we have an outlier, it will just move the centroid in one direction, and it can break down an actual cluster, a natural cluster, to multiple clusters, and we have something like this. To deal with this problem, to handle outliers, first of all, we can use trimming and winterizing like before, but also we can do something else. We can have a new cluster. We can have one additional cluster. If you have one additional cluster, that additional cluster can just go here and can isolate the outlier from the other clusters of interest. So, problem solved. The other problem was with the starting points. Even though we are guaranteed to reach a stable solution every time, the stable solution can be different if we start from different starting points. Now the question is, which stable solution is the correct one or the better one? So which stable solution should we use? For example, here, if we start like with 2 centroids that are up and down, we will end up with these 2 clusters here. But we start with 2 centroids that are left and right, we will end up with clusters that are left and right. So, which clustering is better? That's an important question. To answer this question, we have to understand distortion. Distortion is about the efficiency of the final solution, or is about the performance of the clustering. Here, first we define W of CK, or W of each cluster. W of each cluster is actually sum of the squared distances from all the data points to the centroid of that cluster. All the data points in that cluster to the centroid of that cluster. So let me show you how it is. So let's say we have several clusters here. So we have, let's say, two clusters. We have two centroids, like this centroid and this centroid. The W for the first cluster, let's say two clusters, cluster number 1 and cluster number 2. So W1 is the sum of the squared distances from the centroid of this cluster to all the data points that belong to this cluster. So it is within sum of the squares. Within cluster sum of the squares. It is called within cluster sum of the squares. And so it is W1. W1 is sigma of all these distances squared. W2 is sigma of all these distances squared here. See? And so this is obvious, right? So we have W1 and W2, or W of C1 and W of C2. So based on the number of clusters, we have the number of W's. So at the same number of clusters, we have the same number of W's. So far so good. Now, WSS, or within cluster sums of the squares, is actually sum of the W's, or sigma W. That's it. Sigma W over K. So we have K clusters, we have KWs, and sum of the W's would give us the within cluster sums of the squares. Good? So this is a measure of efficiency or optimality of the result, or of the final solution. The lower the better, right? The lower the better. Now, if we have two competing clustering results, which one do we choose? The one with the smaller WSS. The one that has a smaller WSS will be the optimal solution. And that's it. We solve this problem. And as a result, what we do in most of the clustering techniques, like in R, the function that we use in R, what we do is that we start from several random points, from several random centroids, and then we compare the solutions, we compare the final solutions for the different starting points, and we choose the one that has the lowest WSS. There is also another measure that is between cluster sums of the squares. That's about the distances across clusters. You don't need to learn about that. It's not relevant to what we do. So WSS is good enough. Okay. That was the second concern with clustering using K-bits. The last concern was the optimal number of clusters. How many clusters should we have? Should we have 2 clusters? Should we have 3 clusters? Because we have to decide how many clusters. We have to specify how many clusters before running the algorithm. And to answer this question, again, we are going to refer to WSS. I'm going to explain it now. Let's see an example. So we have these data points, and we have one centroid. Of course, WSS is large. If we have two centroids, if we specify two centroids, the final result would be like this. It's smaller because the distances are, of course, smaller. And then when we have three centroids, of course, it becomes smaller. WSS becomes smaller because the distances are smaller. We have the same number of points, the same number of distances, because we have the same number of data points. But when the number of centroids increases, the distances, the average distances decrease, right? Therefore, what happens is that when we increase the number of clusters, inevitably, WSS decreases. So this is WSS within cluster sums of the squares. And this is with one cluster, then with two clusters, three clusters, etc. As the number of clusters increases, inevitably, WSS decreases, always. So, how many clusters should we use? We use the elbow rule. According to the elbow rule, at the point when the slope changes the most, that's the point that we should, that is the optimal number of clusters. So you see here, we have a sharp decline from one cluster to two clusters. Then we have another sharp decline from clusters to three clusters. But then we have a slight decline from 3 to 4 clusters, etc. So the slope changed here. We have a breaking point here. We have some kind of change here, change in the slope. So we have like this slope, and then we have just a change. And this is a kind of elbow in the diagram. So we see an elbow in the diagram. We should detect elbow point. And that's the optimal number of clusters. That's it. For example, here we have, this is the WSS for one cluster, this is WSS for two clusters, and this is WSS for three clusters. And obviously, the clusters would be optimal. Of course, we can add another cluster, we can add another centroid, and WSS will decrease even further, but is it worth it? Probably not, because the decline, the decrease in WSS is not enough to justify another cluster. Okay? So we probably choose three clusters here. Now, important question that is worth a lot of bonus. So, when we decrease the number of clusters, at what point WSS becomes 0? At what point WSS becomes 0? Or let's put it this way, what is the minimum for WSS? What is the minimum possible value for WSS? As we increase the number of clusters, WSS decreases, right? You see? So when we increase the number of clusters, WSS decreases. At what point it is the minimum for WSS? And why? There will be a question in the exam on this. I'm just telling you. Anybody? there is a guaranteed bonus for this. So I'm just telling you, you will get the full bonus if you answer this question. So, nobody? Okay. So, the minimum is 0, as I mentioned. At what point WSS becomes 0? At what point this will become 0? This is WSS. When all the W's are 0. At what point all the W's are 0? When all the D's are 0. When are all these 0? All the distances 0. Go ahead.
Are whole numbers like technically infinite? So like, would it ever actually reach 0?
Yes, it will reach 0. So the distances can become 0. No? The distances between the centroids and the data points become 0. When the centroids are the data points, the centroids become the data points. That means when K equals N. The number of observations. When K equals N, that's the point where each of the data points is a centroid. Each of the data points is a centroid by itself. So of course the distance between each centroid and its only member is 0. Right? And that's the answer. And after that, if you increase the number of clusters, it's going to stay 0. Of course, it's not an interesting solution, but still, it is a solution and important solution. Okay, let's practice it on R, and then we are going to go to decision trees. First of all, you have access to it. Go ahead.
Like, when would that situation happen where all of the points are centroids?
All the points are centroids. So if you have the same number of clusters as the number of data points, the optimal solution automatically puts the centroids on the data points. Because, you know, let's say you have these data points. Okay, these are the data points. And how many clusters do we have? You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have 10 clusters. You have 10 data points. Let's say you have 10 clusters. If you have 10 clusters, let's say we go to the extreme and say 10 clusters for this small data set. So you put the clusters somewhere, like here, 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 here. But what will happen is that it clusters them like this. The algorithm will cluster based on this, and then so we have our 10 clusters. That is based on proximity. And then what is the next step? The next step is that we find the mean for each cluster. And each cluster happens to have only one data point. So the mean would be that data point. The center of gravity would be just that data point. So the mean would be just the only data point that is in the cluster. So we find the means, and of course the centroids will move to the means for the clusters. So each centroid will move to the mean of the cluster, and the centroids will be on the data points. And that would be the final solution. Zero distances, right? For this example, we are going to use this data set that's about student grades on course using scores.csv. Let's change the directory. And let's see. First of all, we have 100 data points. There is one data set. And it looks like this. As you can see, we have two grades, previous grade and the last grade for each student. We can plot the data like this. So grade versus previous grade. That's the scatter plot. And we want to cluster the students based on grade and previous grade. First of all, we have to scale. We have to scale our data set, or the two variables that we are using for clustering. We can use more than two variables, of course. We are using two variables in this case. And we should scale the variables so they are in level playing field. So, because you know, if the dimensions are different, are hugely different, one of the variables will be ignored. If, for example, one variable is in dollars in revenue, and the other variable is in years, so one variable, the distances with regard to one variable, the deltas with regard to one variable will be like $10 million, $20 million, things like that. And the deltas for the other variable would be 3, 4, 5 years. And when you use the Euclidean distances, one of them will be completely ignored. You know, the distances will be only based on the variable with the larger scale. Therefore, we have to scale the variables so that they are comparable. So to scale the variables, we first get the variables that we need. We need two variables here, the score data. It's just the two variables that we need. And then we use the scale function, as you can see. Use the scale function and it will scale the variables for us, the two variables that we need. Now, I want to make the elbow diagram. We need to install two packages, ggplot2 and also back to extra. After installing these two packages, we use the back to extra and then use this function, if can be cluster. If the scale variables of the function, we specify the method, or we specify the technique for clustering, scalings, and we specify the method, which is WSS. That means we're trying to minimize WSS, or we're trying to compare the results based on WSS. And that's it. We have the elbow diagram. And based on the elbow diagram, it seems to me that the elbow could be 4 or 3. Probably it could be 4 or 3. Sometimes it is difficult to decide. I think must changes in 3. The breaking point is 3. And Okay, let's take 3. Now we want to cluster. We want to cluster a data set for 3 clusters. We use a very simple function called k-means. The first parameter for this function is the escape data, the escape variables. Then the number of clusters or centers, centroids, k, it's k. And then the number of starting points. Remember, I told you that the end result, the stable solution, depends on the starting point sometimes. So if we start from a different centroids, we may end up with different solutions. And at the end, we are going to choose the one which has the lowest WSS, right? So, how can we find the best result or the best starting point? What we do here is that we start with 100 different random centroids and we compare the end solutions. And the end solution that has the lowest WSS will be taken as the optimal solution. Usually it is not necessary, but it's better safe than sorry. Yeah. Okay, let's run the function. The output of this function would give us all the information about the clusters. So Km is the output of the function, the results of the function. So Km equals K-means. We run this. And if we look at the contents of Km, it has all the information about the results of clustering, like the centers, the within SS, that's WSS, that's actually W's, and etc. So let's see what are within SS values. Within SS means just W. Each within SS is W. So $sign within SS will give us 3 numbers, 51, 19, 14. And these are the 3 W's for the 3 clusters. We specified 3 clusters, we specified that we want 3 clusters. So these are the 3 W's for the 3 clusters. And the sum of them would be 85.76. And of course it should match what you see in the next diagram. With the 3 clusters, we are at about 80 something here. You see? So, because this is WSS, and of course it matches what we see in the diagram. Now, we can visualize the clusters. At this point, we have all the information that we need about the clusters. But if you want, we can visualize the clusters as well. Before visualizing them, let me show you the results of the clusters. These are the cluster scores. As you can see, each student is assigned to a cluster. Cluster 1, 2, 3, 1, 3. Just attach the matrix, attach the list of clusters to the list of students. Attach them using the cbind function. We attach them, and we have the students next to the clusters. And then we can, if we want, we can order the students based on the number of clusters, the cluster numbers, and we can see the students like this. So order based on their cluster numbers. So we have the students in the first cluster here, see cluster number is 1, and then we have the students in the second cluster here, and then we have the students in the third cluster. See, the cluster is the last column in this combined data frame because we attached the cluster column to the students data set or to the students data frame. Now, let's visualize the results. Visualize the results. We can just do this. We can just run this command, fb's cluster, and the result would be like this. So the red data points, the red students are in one cluster, the green students are in another cluster, the blue students are in another cluster. So we have 3 clusters. And to visualize, you can just run this command, fb's cluster. Kn is the output of the k-means command, of the k-means function. You use the output of the k-means function as the first parameter for visualization. Then you give the data to it again, and then